In this video, we're going to focus on Newton's three laws of motion. We're going to cover forces, normal force, tension, pulleys, static and kinetic friction, and a lot of other stuff too. So let's begin. So what is Newton's first law of motion? The first law of motion is an object at rest will continue at rest, and an object in motion will continue in motion unless acted on by a force. So let's say if you have a horizontal frictional surface. If you roll a ball along the x-axis, that ball will continue to move at its original speed. Let's say if it's moving at 15 meters per second. If there's no friction, it's going to continue to move at 15 meters per second forever along the x-axis without changing direction. Now in reality, we know there's friction, so there is a force that acts on it, which eventually slows it down. But if there was no friction, it would keep moving forever. Just think about an object in space. An object in space that is not acted on by any forces will just keep on moving in a straight path. And so that's the main idea behind Newton's first law of motion. An object in motion will continue in motion unless acted on by force. Newton's first law of motion is also known as the law of inertia. Now you might be wondering, well, what exactly is inertia? Inertia is the tendency of an object to maintain its state of rest or uniform motion. Inertia is related to mass. As the mass of an object increases, the inertia increases as well. So let's say if we have a 100 kilogram object and a 1,000 kilogram object. Which one has more inertia? So which object wants to maintain its state of rest? If we apply a force to the smaller object, it's going to be relatively easy to move. We can easily move it from a state of rest. Now the larger object, it's going to be difficult. To get it going, it requires a greater force to move it. So it's harder to move it from a state of rest. So the more massive object has more inertia. And so that's the main idea behind inertia, which is the tendency of an object to resist or maintain its state of rest. It's going to resist any changes in motion that you try to apply to it. Now the next law that you need to be familiar with is Newton's second law. Newton's second law is basically this equation. Force is equal to mass times acceleration. And this, of course, is the net force. So let's say if you have a mass of 5 kilograms and the acceleration on it is 2 meters per second squared. The force is 10 newtons. And this is the net force. A newton is equivalent to 1 kilogram times a meter over second squared. It turns out that the newton is not the only unit for force. Force can be measured in pounds. It turns out 1 pound is approximately 4.45 newtons. So now you know how to convert from newtons to pounds. So let's say if you have about 100 newtons. How many pounds of force does that represent? So to convert it, let's use the conversion factor that I just gave you. So we said that there's 4.45 newtons per pound. So you want to set it up in such a way that the unit newtons cancel. So to convert newtons into pounds, simply divide the force by 4.45. And you should get 22.5 pounds approximately. Now what is the weight force? What's the difference between mass and weight? Mass is measured in units of kilograms. So in physics, whenever you see kilograms, it's associated with mass. Weight is different from mass. Weight is a force, and so weight is measured in newtons, sometimes pounds. Weight is equal to mass times gravitational acceleration, the same way as force is equal to mass times acceleration. As you can see, these two are the same. When you see g, g is a type of acceleration, and weight is a type of force. Weight is simply the force of gravity that is acting on you. And so weight is a downward force. Consider this 20 kilogram object. What is the weight force acting on it? Go ahead and calculate it. So the weight force is always equal to mg, mass times gravitational acceleration. And on Earth, the gravitational acceleration is 9.8 meters per second squared. So this is going to be about 200. You could round that to 10 if you want, but let's use the exact value. So 20 times 9.8 is about 196 newtons. So that's the weight force. Now consider an object that is placed on the surface of the Earth and an identical object that is placed on the surface of the Moon. These two objects, do they share the same mass or the same weight? And what really is the difference between mass and weight? So let's say if the mass on the Earth is 100 kilograms. Will the mass of the object be the same on the Moon? Mass is the quantity of matter. So the object is going to have the same number of atoms on the Earth and on the Moon. So the mass is going to be the same. It's going to be 100 kilograms. Weight is not the quantity of matter. Weight is a force. And weight is dependent on gravitational acceleration, which is different on the Earth than it is on the Moon. On the Earth, you will feel heavier. The gravitational acceleration that you would feel is 9.8 meters per second squared. On the Moon, g is about 1.6. So you would feel lighter on the Moon. You can jump higher on the Moon because the gravitational acceleration is much less. On the Earth, you can't jump that high. So if you were to calculate the weight force of this object, on the Earth, it's going to be 100 times 9.8. So it's 980 newtons. On the Moon, it's 100 times 1.6. So it weighs 160 newtons. Now, what is Newton's third law of motion? Newton's third law of motion states that for every action force, there is an equal but opposite reaction force. So let's say if you have two people skating. I'm just going to draw stick figures. And one person has more mass than the other person. So if the smaller person applies a force of 100 newtons on the larger person, what force will the larger person apply on the smaller person? According to Newton's third law, for every action force, there is an equal but opposite reaction force. So the other person is going to apply a force of 100 newtons. They have to be equal, but they're opposite in direction. So the forces are always the same. You might see a question like this on the test. Just remember the forces are equal and opposite in direction. Now, let's say if the mass of the smaller person is 50 kilograms and the mass of the larger person is 100 kilograms. Who experiences the greater acceleration? And who's going to move further? Let's say if they're on ice. So as each of these individuals, as they push against each other, they're going to move apart. This person's going to move this way, the other person is going to move that way. However, the acceleration is not the same. If you use the equation F is equal to ma, the force acting on the smaller person is 100, and he has a mass of 50 kilograms. So solving for the acceleration, you can see that he's going to experience an acceleration of 2 meters per second squared. Now, the person on the right, he's going to experience a small acceleration because he has a larger mass, he has more inertia. So it's going to be harder to move the larger person. So using equation F is equal to ma, he experiences a force of 100, but since he has a mass of 100, the acceleration is going to be 1. So because he experiences a small acceleration, he's not going to move very far. The smaller person, he's going to move a lot further than the larger person because he's smaller and he experiences a greater acceleration. So on ice, if you see two people pushing against each other, they experience the same force, but the smaller person is going to fly away to the other side, and the larger person, he's not going to move back very much since he experiences a small acceleration. Another example of Newton's third law is the force of gravity that acts between the Earth and the Moon. So what is gravity? What is gravitational force? Gravity is a force that brings matter together. So the gravitational force between the Earth and the Moon, it pulls the Earth and the Moon toward each other. So the Moon is attracted to the Earth, and the Earth is attracted to the Moon. Because of gravity, the Moon remains in orbit around the Earth. So the Moon has a tangential velocity where it wants to fly off into outer space, but the force of gravity that acts on the Moon by the Earth keeps it in orbit. Now, these two forces, are they equal or are they different? Is the gravitational force on the Earth greater than that on the Moon? Or is the gravitational force on the Moon greater than that on the Earth? Or are they the same? So according to Newton's third law, these forces are the same. Even though the mass of the Moon is much less than the mass of the Earth, the forces are still equal. These are equal and opposite forces. Notice that the direction is opposite. This one appears to be moving to the right, and this one is moving to the lower left. But the forces share the same magnitude. Now, which one has the greater acceleration? Is it the Earth or the Moon? Now, because the Earth has more mass, it's going to have a smaller acceleration. So it's going to have a low acceleration value. The Moon, because it has less mass than the Earth, has a higher acceleration value. So unless the masses are the same, then the acceleration is going to be the same. But if the masses are different, then the acceleration will also be different. The object with less mass has more acceleration, and the object with more mass has less acceleration, but the forces are always equal. Another example of Newton's third law in action is a rocket. Here's a question for you. How does a rocket propels itself upward? I'm just going to draw a generic shape. A rocket propels itself upward by exerting a force on the gases that are expelled. So the gases that are expelled, it leaves the rocket in a downward direction. And by exerting a force on that gas, it also exerts an upward force that propels the rocket above the ground. And so the rocket goes up. And an object in space, let's say if you have a rocket in space, that's how it works too. in order for the rocket to move in space, it has to exert a force on a gas, propelling the gas outward, and so the rocket will propel in a forward direction. So if you want the rocket to move, let's say, to the right, you need to shoot out gas to the left, and that's going to cause the rocket to move to the right. And so these two forces are equal and opposite in direction. So that's another example of Newton's third law. Another way you can see this in a practical situation, let's say if you're in the ocean on a boat. If you take a package and if you throw it, let's say to the right, you're going to feel a recoil. You're going to feel a force that pushes you back the other direction. So by throwing the packet to the right, you're going to move to the left. So you are going to propel the boat, and together, both of you are going to move to the left. Now, granted, the mass of the package is much less than the combined mass of you and the boat. Therefore, since the package has less mass, it's going to experience a greater acceleration, and so it's going to move a larger distance to the right. Now, because you and the boat have a much greater mass than the package, you're going to experience a smaller acceleration. So you're going to move to the left, but not by much. You're going to move to the left just only a significantly smaller distance. And so that's another example of Newton's third law. And there's one more example that you need to know, a very important one too. So let's say if we have a horizontal surface and an object on a surface. Let's say we have an object that has a mass of 100 kilograms. So if you place a block on a surface, it's not going to move. It's just going to sit there. How can you draw a free body diagram showing all the forces that are acting on this box? So the box exerts a downward force on the surface. We know that because gravity is acting on the box. So the box, it feels a weight force that is equal to mg, or that's 100 times 9.8, which is 980 newtons. So if the box, or if the block, exerts a force on the surface, then according to Newton's third law, the surface must exert the same force on a block, especially if there's no net force, if the block is at rest. The force that the surface exerts on a block is an upward force, and it's called the normal force. The normal force is exerted by the surface, and it's always perpendicular to the surface. It's always at a 90-degree angle with respect to the surface. This normal force has to be equal to the weight force. The surface has to support the weight of the object, so it has to exert a force that's equal to the weight of the object. And as you can see, this proves Newton's third law. For every action force, there is an equal but opposite reaction force. The normal force is also known as a contact force because it will only exist when two surfaces are in contact with each other. So if the block is not in contact with the surface will not exert a normal force on a block. And so that's why it's called a contact force. Now here's a question for you. How can you increase and decrease the normal force on this object? So right now, we know that the normal force is 980. But how can we increase that value, and how can we decrease it? So feel free to pause the video and think about it, and then unpause it when you have the answer. So here's a question for you. What's going to happen if you press on the block? So let's say if you apply a downward force of 300 newtons. What force will the surface exert on the block? So if you have to apply a downward force of 300, the surface, does it have to work harder to lift the block or keep it where it is? Or is it easier for it to maintain the block on its surface? So notice that the surface has to work harder. Not only does it have to support the weight of the block, but it also has to support the downward force that you apply on the block. So the normal force is greater. So the surface must exert a force of 1280 newtons so that the object will remain at rest. Because if you press on the block is not going to move down. It's not going to break through the surface unless you have a very weak surface. But if the surface is strong enough, it's going to support the weight of the block and a downward force that you apply to it. So anytime you press a block on a surface, you increase the normal force. So now, how can we decrease the normal force? What is a practical way in which we can relieve the stress on a surface? The best way to do that is simply to apply a force in the opposite direction, and that is to lift up the block. If you attach a rope to the block, you can pull it up with an upward force. But let's say if you apply an upward force that is less than the weight of the object. So let's apply an upward force of 400 newtons. So now what is the net force, or not the net force, but what is the normal force that the surface exerts on the block at this point? So if you exert an upward force of 400, the surface doesn't have to work as hard to support the weight of the block. It only needs to apply an upward force of 580 newtons. Now, to calculate this answer, here's what you can do. You can set up an equation. I might need more space, so let's put this somewhere else. The net force in the y direction is equal to the sum of all forces in the y direction. So we have an upward force of 400 newtons. By the way, the force that acts on a rope, what is that called? Anytime you have a force that acts through a rope, it's also known as the tension force. So the tension force is 400. Now there's two forces in the upward direction. That's the normal force and the tension force. Because it's going in the positive y direction, these two forces are positive. Now the weight force is directed in the negative y direction. So we're going to put minus w. Now because the block remains at rest, the net force acting on it is 0 because it's not accelerating upward or downward. It's maintaining its position. So the normal force plus the tension force minus the weight is equal to 0. So if we solve for the normal force, if we move negative w from the left side to the right side, it's going to change to positive w. And if we move positive t from the left side to the right side, it's going to change from positive t to negative t. So the normal force is a difference between the weight force and the tension force. And as you can see, it's 980 minus 400. So the normal force is about 580 newtons in this example. If the tension force exceeds the weight force, the object will begin moving upward. It's going to experience an upward acceleration. And so there's not going to be any normal force. Now that we're on the subject of tension, let's talk more about it. So let's say if we have a mass of 100 kilograms. What is the tension force that's needed to support the weight of the object. Let's say if the object has an acceleration of 0, so it's not moving up, it's not moving down, it simply remains at rest. What is the tension force? In addition, let's say that's part A. The object is at rest. Calculate the tension force if the object is moving upward at a constant speed of 3 meters per second, and if it's moving downward at a constant speed of, or let's say a velocity of -2 meters per second, and if it's accelerating upward at 2 meters per second squared and downward at -3 meters per second squared. Calculate the tension force on the rope under each of these circumstances. Let's begin by calculating the weight force. So the weight force, which is mg, it's 100 times 9.8. So the weight force is 980 newtons. So in part A, for the object to maintain its position, for it to remain at rest, the acceleration has to be 0, which means the tension force must be strong enough to support the weight of the object. So for part A, the tension force is 980 newtons. That makes sense, right? These two have to be equal and opposite in direction if the object is going to remain at rest. Now here's a question for you. Is it easier to lift up the object or to slowly let it fall down? Which one is easier and which one is harder? Is it harder to lift it up or bring it down? Now imagine if you're going grocery shopping and you have a gallon of water or a gallon of milk and you wish to lift it up on the counter. It's going to take a lot more effort to lift up the gallon of milk. Now if you have it now in your hand and you wish to lower it to the ground, it's easier to do that, but it requires more effort to lift it to the counter. So likewise, the tension force is going to be greater than 980 if you wish to lift the object up with an acceleration. If you want to bring it down, it's going to be much less. The weight force, the tension force is going to be less than 980 if you need to lower the object in the downward direction. But to lift it up, the tension force has to be greater than 980. So let's find an equation that can help us to calculate the tension force under each of these circumstances. The first thing that we need to do is we need to write an equation that represents the sum of all forces in the y direction. So it's going to be the tension force minus the weight force. Because the tension force is directed in the upward direction, it's going to be positive. And the weight force is directed in the downward direction, so it's negative. The sum of the forces in the y direction is also equal to the net force. So net force is tension minus the weight force. And the net force is equal to ma. So the mass times the acceleration is tension minus the weight force. Now keep in mind, according to Newton's second law, F equals ma, so that's why we can replace the net force with ma. Now the weight force is equal to mg. So let's add mg to both sides. So ma plus mg is equal to the tension force. So if we factor out the GCF, the greatest common factor, which is m, the mass times the acceleration plus g is equal to the tension force. So this is the equation that you need for this particular situation. So for part A, the acceleration is 0 and the mass is 100. So we could see why the tension is 100 times 9.8 and it's 980, which conceptually we got that answer. Now what about parts B and C? In part B, the velocity is positive 3. It's moving up at a constant speed of 3 meters per second. So at constant speed or even constant velocity, what is the acceleration? The acceleration is the rate of change of velocity. So if the velocity is not changing, then the acceleration is 0. So for B and C, if it's moving up at constant speed or down at constant speed, the acceleration is 0 and the tension force remains at 980. Now for D and E, it's different. If the block is accelerating in the upward direction, the tension force is going to be greater than 980. The tension force has to support the weight of the object, plus it has to accelerate the object upward. So that requires more work. So using the equation, it's going to be 100 times 2 plus 9.8, or 100 times 11.8, which is 1180. So it takes a lot more effort to accelerate the object in the upward direction. Now what about the downward direction? It's going to be easier, because you don't have to lift the object, you simply have to let it go slowly as it descends downward. So for part E, the acceleration is negative 3 plus 9.8. So negative 3 plus 9.8, that's the same as 9.8 minus 3, which is 6.8. So if it's descending at a rate of negative 3 meters per second squared, the tension force is less, it's 680. Now there's one topic that I would like to revisit, and I need to clarify something. So let's say if you have a person and he throws a basketball. He exerts a force of 100 newtons on a basketball. He's going to feel an opposite force or recoil force of 100 newtons. So notice that these two objects are going to separate. The person is going to move to the left, the basketball is going to move to the right. And so this is a good example of Newton's third law. These are action and reaction pairs. And notice that these forces are acting on two different objects. Now you have to be careful though, because let's say if you have a block on a table, let's say it's 100 kilograms, even though the weight force is equal to the normal force, these are not true action-reaction pairs, even though they work the same way. The weight and the normal force in this particular example are equal in magnitude and opposite in direction. However, they don't move apart in the same way as these two objects do. And also, these forces are acting on the same object. The weight force and the normal force are acting on the 100 kilogram object, so it remains at rest. Whereas, if you focus on a basketball, only one force is acting on it, and the other force is acting on the other person to move them apart. So, even though this example, it appears as if the weight force is the action force and the normal force is the reaction force, these are not true action and reaction pairs, because these forces are acting on the same object. So I just want to clarify that particular concept. Now let's say if you have a force of 50 newtons directed to the right, plus another force of 100 newtons directed to the right. What is the net force? Whenever you have two vectors that are parallel to each other pointing in the same direction, the net force is the sum of these two vectors. So it's going to be 150. Now what about having two vectors in the opposite direction? So if you have a 100 Newton force directed to the right and a 20 Newton force to the left, what's the net force? How can you add these two vectors? So it's going to be 100 minus 20, so it's 80 newtons. Now what if you have a force of 30 newtons directed to the right along the positive x-axis and another force of 40 newtons directed in the positive y-axis. What is the net force? What is the magnitude of the net force, and also the direction of the net force? To find it, whenever you want to add two vectors that are perpendicular to each other, you can draw a triangle. So let's call this f of x, f of y, and this is f, the magnitude of the net force. And here's the angle of f relative to the x-axis. So we got to find the hypotenuse of the triangle. Since we have a right triangle, we can use the Pythagorean theorem. C squared is equal to a squared plus b squared. And so the hypotenuse c is the square root of a squared plus b squared. Therefore, the magnitude of the force is the square root of f of x squared plus f of y squared. So in this case, it's the square root of 30 squared plus 40 squared. Now, there are special triangles to know, like the 3, 4, 5 triangle, the 5, 12, 13 triangle, the 8, 15, 17, and the 7, 24, 25. So, if this is 30, and if this is 40, the hypotenuse must be 50. It's based on the 3, 4, 5 triangle. 30 squared is 900, 40 squared is 1600. When you add them, you get 2500. And if you wish to take the square root of 2500, separate it into 25 times 100. The square root of 25 is 5, the square root of 100 is 10, and so you get 50. Now let's say if you wish to find the angle relative to the x-axis. How would you do it? To find the angle, you need to use tangent. Perhaps you heard of the expression SOHCAHTOA in trig. Sine is opposite over hypotenuse, that's the SO part. The CA represents cosine is adjacent over hypotenuse, and tangent is opposite of adjacent. Relative to theta, Fy is opposite to it, Fx is adjacent or next to it, and the hypotenuse is always across the box. So tangent theta is equal to O over A, opposite over adjacent, so f of y divided by f of x. So theta is equal to the inverse tangent of f of y divided by f of x. So inverse tangent of 40 divided by 30 is about 53.1 degrees. So that is the direction of the force vector F. So now what if you have two vectors that are not parallel or perpendicular to each other? How can you add them? So let's say if you have a force of 100 newtons and you wish to add it to another force of, let's say, 200 newtons. That is 30 degrees above the horizontal. What is the net force? Go ahead and calculate the magnitude of the net force and the direction. Now here's a standard way of solving these types of problems. Let's call this f of 1 and f of 2. What you want to do is you want to find f of 1x and f of 1y, and also f of 2x and f of 2y. But let's write the equations for these first. So let's redraw the triangle that we had in the beginning. Let's say this is f of x, f of y, and f. Sine theta, based on SOHCAHTOA, is equal to the opposite side divided by the hypotenuse. So that's the SO part in SOHCAHTOA. O is for opposite, H is for hypotenuse. So sine theta is f of y divided by f. So f of y is f sine theta. Remember this equation. Now cosine theta, this is the CAH part of SOHCAHTOA. Cosine theta is equal to the adjacent part divided by the hypotenuse. So that's f of x divided by f. Now, if you multiply both sides of the equation by f, you'll see that f of x is equal to f cosine theta. So remember this equation too. So to add these two vectors, we need to find f1x and f1y, and we also need to find f2x and f2y. So f1x is 100 cosine 0. The reason why it's 0 is because the angle is 0 degrees along the x-axis. It's 90 along the y-axis. This is 180 and this is 270. So cosine 0 is 1. 100 cosine 0 is going to be 100. Because this force is directed along the x-axis, it's completely f of x. There's no y component. f1x is f1 because it's purely horizontal. If you try to calculate f1y, it's going to be 100 sine 0. Sine 0 is 0, so you're going to get 0. The reason being is this vector is horizontal. There's no y component. It doesn't go up or down. Now, f of 2, however, is at an angle, which means it has an x component and it has a y component. To find f2x is going to be f2 cosine 30. If you type that in the calculator, 200 cosine 30, you should get about 173.2. And because f of x is going to the right, it's along the positive x-axis. F of 2x is positive. Now, f of 2y, that's going to be 200 sine 30. Sine 30 is about a half, so 200 sine 30 is equal to 100. Now, because this part is going up along the positive y-axis, f2y is positive 100. So what we need to do is add the x components and the y components together. F of x is going to be 273.2, and f of y, if you add them, is simply 100. Now keep in mind, f is the square root of f of x squared plus f of y squared. So what we have is the square root of 273.2 squared plus 100 squared. And that is going to be about, I'm going to round it to 291 newtons. So that's the magnitude of the net force. Now let's understand why we can use that equation. The resultant force is basically the distance between these 2 points. Whenever you wish to add two vectors, draw the first vector and then draw the second vector from head to tail. So if this is f1 and this is f2, the resultant vector is right here. This is the initial point, and the arrow is going to point to the final position. So to find FR, you can also find it this way. You can redraw f of 1 and f of 2. Instead of drawing f of 2, you can draw f of 2x and f of 2y. And then this is f of r, which is the hypotenuse of this triangle. So f of 1x, which is the same as f of 1 plus f of 2x, this distance, that's 100 plus the 173. So the x part of the triangle is 273.2. The y part of the triangle, which is f of 2y, that's 100. So that's why we were able to use the Pythagorean theorem to calculate f of r. Now the last thing we need to do is find the angle. So here's the angle theta. So theta is the inverse tangent of f of y divided by f of x. So it's going to be the inverse tangent of 100 divided by 273.2. And so the angle for this example is about 20.1 degrees. Now let's try one more example for the sake of practice. So let's say if you have a force which has a magnitude of 300 newtons and it's 30 degrees above the negative x-axis. And there's another force, we'll call it F2, which is 200 newtons along the negative y-axis. Calculate the resultant force. Find a magnitude and a direction. So, let's begin. We need to find F1x and F2x. And we also need to find F1y and F2y. So if we focus on F2, it's going in a negative y direction. Keep in mind, this is 0, 90, 180, 270. So the angle in the negative y direction is 270. So to find f of 2y, it's going to be 200, which is the magnitude of f of 2, times sine of 270. Sine 270 is negative 1, so this is negative 200. The negative sign tells you that it's going in the negative y direction. Now, because this vector is completely in the y direction, it's a straight line. It's not at an angle like this. There's no horizontal component. F of 2x is 0. If you type in 200 cosine 270, cosine 270 is 0, so that's going to be the value of f of 2x. Now let's focus on f of 1. F of 1 is going in this direction, and it has a magnitude of 300 newtons. So if we draw a triangle, we have a 30-degree reference angle, and we could find f of 1x and f of 2x. So f of 1x is going to be 300 cosine 30. 300 cosine 30 is about 259.8. Now notice that this is going in the negative x direction. f1x is going to the left. So therefore, f of 1x is negative. If you find the angle relative to the positive x-axis, the angle is 150. This is 180. So this is 30. This has to be 150. If you type in 300 cosine 150, you should get negative 259.8. So f of 1x is simply negative. That's what you need to take from this. Now what about f of 2y? I'm thinking I wrote f of 2x, but that was supposed to be f of 2y. So f of 2y is going to be 300 sine 30. Sine 30, we know it's a half, so this is going to be 150. And because f of 2y is going up in the positive y direction, this should be positive. If you type in 300 sine of 150 degrees, you should get positive 150. So now let's add the x components together. So f of x is negative 259.8. And let's add the y components. 150 plus negative 200, that's negative 50. Now what I would do is redraw what we have. So let's say if this is the origin. F of x is negative, so we need to move to the left by negative 259.8 units. F of y is negative, but it's smaller, so we have to go down by negative 50. So this is the origin, and so we have a triangle in quadrant 3. Keep in mind, this is the first quadrant, this is the second quadrant, this is quadrant 3, this is quadrant 4. So this is the reference angle. So now we could find the magnitude of the resultant force. So the resultant force is going to be the square root of negative 50 squared plus negative 259.8 squared. So you should get a resultant force of 264.6 newtons. For those of you who need to do some calculations like this without a calculator, notice that the resultant force is very close to this value. For this equation, when one of the values is significantly larger than the other, the resultant force is going to be approximately equal to the larger value. So notice that it's very close to 260. Because 50 squared is much smaller than 260 squared. So that's why the final answer is very close to 260. So that's the magnitude of the resultant force. It's 264.6. Now the next thing that we got to find is the angle. So first, let's calculate the reference angle. Keep in mind the angle inside the triangle is the reference angle. The actual angle that we need is the angle measured from the positive x-axis, which we'll get soon. To calculate the reference angle, it's going to be the inverse tangent of f of y divided by f of x. So that's inverse tangent. Don't worry about the negative signs. Either case, the two negative values will cancel and it's going to be positive. But if it's in quadrant 2 and 4, plug in the positive values. Don't put the negative values into this equation. Calculate the reference angle, and then based on the quadrant, you can figure this one out. So inverse tangent y over x, that's 50 divided by 259.8. So you should get an angle of about 10.89 degrees. So that's the reference angle. Let's calculate the actual angle. So let's say it's about 10.9. From here to here is 90, then it's 180, and then it's 180 plus 10.9. So that angle, measured from the positive x-axis, is about 190.9. So that is the direction of the force vector, or the resultant vector, from the positive x-axis. If you want to measure from the negative x-axis, it's simply 10.9 degrees below the negative x-axis. So going from the positive x-axis to the angle, this is 190.9 degrees, what we can say counterclockwise from the positive x-axis. Now if you choose to go this way, that's going to be 360 minus 190.9. So that's the same as going 169.1, but clockwise, in the direction of a clock, from the positive x-axis. So you have different ways of describing the location of the resultant vector. Now let's get back to tension. So let's say if we have a horizontal surface and we have two blocks connected by a rope. And let's exert a force of 60 newtons to the right. And let's say the mass of the first object is 10 kilograms and the mass of the second object is 20 kilograms. What is the tension force in this rope? What is the answer? Now, the tension force in a rope that pulls the 20 kilogram object to the right is equal to 60 newtons. Now, to find the tension force in a rope, we need to find the net acceleration of the system. So we can treat these two objects as if it were a single mass of 30 kilograms. So using this equation, F is equal to ma. We have a net force of 60 newtons, a total mass of 30 kilograms. So the net acceleration is 2 meters per second squared. Because these two objects are attached by a rope, if the 20 kilogram object moves with an acceleration of 2 meters per second squared, the 10 kilogram object must accelerate at the same rate because they're attached to the same rope. And so they're going to move at the same speed along this horizontal surface. Now let's focus on the 20 kilogram block. Let's isolate it. The 20 kilogram block, it feels a force of 60 newtons that propels it to the right. It also feels a tension force that slows it down. That tension force is caused by the 10 kilogram object. To pull the 10 kilogram object to the right, the 20 kilogram object experiences a reaction force that pulls it to the left. And that's the tension force. And we also have a net force because the 20 kilogram object accelerates to the right. So how can we write an equation for the net force for the 20 kilogram object? So the net force for the 20 kilogram object, which is the forces in the x direction, is the force that propels it to the right minus the tension force that pulls it to the left. So the net force is ma, and F is 60, and we're looking for T. Now the mass times acceleration, 20 times 2, the net force acting on the 20 kilogram block is 40 newtons. So therefore the tension has to be 20. 60 minus 20 is 40. So this 20 kilogram block feels the tension force of 20 newtons. Now notice that this tension force that pulls the 20 kilogram block to the left is equal to the tension force that pulls the 10 kilogram object to the right. And notice that this tension force is also the net force. The only force that acts on a 10 kilogram object is the tension force. And so that's equal to the net force of 20. 10 times 2, m times a, is 20. So everything matches, everything works out. So I want you to understand this. For the 20 kilogram block, it feels a force of 60 newtons that pulls it to the right, and a tension force of 20 newtons that slows it down to the left, and so you have a net force of 40 newtons that propels it to the right. This time, let's say if there's 3 blocks. Let's say the mass of the first block is 30 kilograms, and for the second block it's 20, and for the last one it's 10. And the force that pulls all of them together, let's say it's a force of 180 newtons. Calculate the tension force in these two ropes. So the first thing we need to do is find the acceleration. So the net force of 180 is equal to the total mass times the net acceleration. The total mass of the system is 60 kilograms. So 180 divided by 60 is the same as 18 over 6 if you cancel the zeros. 18 divided by 6 is 3. So the acceleration is 3 meters per second squared. Now once you have the acceleration, calculate the net force acting on each object. So starting with the first block, 30 times 3 is 90. So the net force acting on this block is 90 newtons. 20 times 3 is 60. So this block experiences a net force of 60 newtons. 10 times 3 is 30. So this is going to move with a net force of 30 newtons. So now we can calculate the tension force. The tension force that pulls the 30 kilogram block to the left is the difference of these two forces. So 180 minus 90 is 90. The tension force that pulls the 20 kilogram object to the right is equal to the tension force that pulls the 30 kilogram object to the left. So they're both 90. So the 20 kilogram object feels a force of 90 newtons that pulls it to the right. So with that information, we can calculate the tension force that pulls the 20 kilogram object to the left. And so it's going to be 90 minus 60, which is 30. So we have a tension force of 30. And that tension force is equal to the tension force that pulls the 10 kilogram block to the right, which is 30. And that tension force is equal to the net force on this block because there is no force that pulls the 10 kilogram block to the left. So therefore, for the last one, the net force on the last block is equal to the tension force in this rope. So the answer to this problem, the tension forces are 30 and 90. So now it's your turn. Try this example. Let's say if you have 4 blocks. Calculate the tension force in each block. And let's say the force is 500 newtons. This is going to be a 40 kilogram object. This is 30, 20, and 10. So feel free to pause the video and work out this example. So the first thing we need to do is find the overall acceleration. So net force is equal to ma. The net force is 500, and the total mass of the system is 40 plus 30 plus 20 plus 10, and that's 100 kilograms. So 500 divided by 100, the net acceleration is 5 meters per second squared. So let's calculate the net force acting on each object. So for the first object, it's 5 times 10, so it feels a net force of 50. For the second object, 5 times 20, that's a net force of 100. For the third object, 5 times 30, that's 150. And the last object feels a net force of 40 times 5, which is 200. So to find a tension force, subtract these two forces. 500 minus 50 is 450. So there's a tension force of 450 newtons directed to the left on the 10 kilogram block, which means that the 20 kilogram block feels a tension force of 450 that accelerates it to the right. Now, 450 minus 100 is 350. So the 20 kilogram block, it feels a tension force of 350 that slows it down, which means that the 30 kilogram block experiences a tension force of 350 that pulls it to the right. So 350 minus 150 is 200. So therefore, the 30 kilogram block feels a tension force of 200 that slows it down. And a 40 kilogram block feels a tension force of 200 that pulls it to the right. And that tension force is equal to the net force. So that's how you know if you did it correctly. The net force and the tension force must be the same on the last object, because there's nothing that pulls the last object to the right. Here's another problem that you might see. Let's say if you have a block supported by 2 ropes and it's suspended in the air. Let's call the first rope T1 and the second one T2. And let's say T1 makes a 30-degree angle with the vertical, and T2 makes a 60-degree angle with the vertical line. And the mass of the block is 20 kilograms. With this information, how can you calculate the magnitude of the tension forces T1 and T2 that can support the weight of the block? Feel free to pause the video and work out this example. So we need to draw a free body diagram. We need to represent, or we need to show all the forces that are acting on that block. So what we have is really just the weight force, which is mg. But we also have the component forces of T1 and T2. So we also have T2x, which cancels out T1x. And we also have T2y and T1y, which together supports the weight of the block. So the sum of the forces in the x direction is T1x and T2x. T2x is positive because it's going to the right. T1x is negative because it's going to the left. And because the block is static, because it's at rest, it's not moving, it's stationary, the net force in the x direction and in the y direction must be equal to 0. So if T2x minus T1x is equal to 0, we can take this and move it to this side. And therefore, T2x is equal to T1x. Now, the weight has to be supported by T2y and T1y. So T1y plus T2y should be equal to mg. So we could say that the sum of the forces in the y direction is equal to positive T1y because it's going up, plus T2y minus mg because the weight force is going down. And because the object is at rest, it's not accelerating anywhere, the net force is 0. If we move mg to the other side, it's going to be positive. So therefore, we could say that T1y plus T2y is equal to mg if we focus on this side and this side of the equation. We don't need to worry about this anymore. So how can we use this information to solve for T1 and T2? So whenever you need to find 2 variables, you need 2 equations to solve it. You need a system of equations. So let's focus on T2x and T1x. T2x is T2 cosine theta. Now the angle that we need is this angle, which is 30, because cosine 30 is adjacent over hypotenuse. So we don't want to use the 60. Otherwise, it will have to be sine 60. Sine 60 is opposite over hypotenuse. So let's use the 30. So T2 cosine 30 is equal to, now for T1x, let's use the 60, because that's really the standard angle that is close to the x-axis. Cosine 60 is adjacent over hypotenuse. So T1x is T1 cosine 60. So let's get T2 in terms of T1. So if we divide both sides by cosine 30, T2 is T1 cosine 60 divided by cosine 30. Cosine 60 divided by cosine 30 is root 3 over 3, which is 0.5774. So we could say that T2 is equal to 0.5774 T1. So let's save this equation now that we have T2 in terms of T1. So now let's work with the other equation. T1y plus T2y is equal to mg. So somehow we got to get T1 and T2. So we know that T1y is T1 sine theta, and theta is 60. 60 is opposite to T1y. So T1 sine 60 plus T2y, which is T2 sine 30, is equal to mg, which is 20 times 9.8. And that's about 196. Sine 60 is root 3 over 2, which as a decimal, it's about 0.866. So we have 0.866 T1. T2 is 0.5774 times T1, and sine 30 is a half, and this is equal to 196. So we have 0.866 T1. Actually, there's probably not enough space there. Plus 0.5 times 0.5774. That's 0.2887 T1. So now that we have like terms, we can add 0.866 with 0.2887. So we now have 1.1547 T1 is equal to 196. (196) divided by 1.1547. That'll give you a T1 value of 169.74. So that's the tension force in the first rope. To find the tension force in the second rope, we can use this equation. So T2 is going to be 0.5774 times the value for T1, which is 169.74. And you should get about 98 newtons. So that's how you can calculate the tension forces that are needed to support the weight of the block. The key is to write the equation for the sum of the forces in the x direction and in the y direction. And once you have two equations using the x and y components of T1 and T2, you want to get T2 in terms of T1 using one of the equations. And then plug this into the second equation so that you can only get either T1 by itself or T2 by itself, and then you could solve it. Here's a question for you. Let's say if you have two blocks. We'll call the first block Block A and the second one Block B. Now let's say that Block A has a mass of 20 kilograms and Block B has a mass of 10 kilograms. And we're going to exert a force on Block A that has a value of 90 newtons. So here's the question. What is the force that A exerts on B, and what is the force that B exerts on A? this problem is similar to the tension problem where we had a bunch of blocks connected by ropes along a horizontal surface. Let's find the net force. Well, actually, let's find the net acceleration. So the net force is equal to ma. The net force is 90. That's the total force that we're applying to both blocks. The total mass is 30, so the acceleration of the system is 3 meters per second squared. So if this was a single block of 30 kilograms, the whole system is moving at an acceleration of 3 meters per second squared. Now, what's our next step? What do we have to do at this point? Our next step is to find the net force on each block. So it's going to be m times a. Let's multiply the 20 kilogram mass by 3 meters per second squared. So the net force acting on block A is 20 times 3, which is 60 newtons. The net force acting on block B is m times A, 10 times 3, which is 30 newtons. So now let's focus on block A. If the net force is 60 and we're applying a force of 90, that means that there's a force of 30 newtons that is opposing A. If we have 90 newtons going to the right and 30 going to the left, that's going to give us a net force of 60. Now if we focus on B, B has a net force of 30. There's no force that goes against B to the left. We're going to assume that the surface is frictionless. So the only force that propels B to the right is the force that A exerts on B, which is 30 newtons. So notice that the force that B exerts on A is this force. B slows down A, so to speak. So B exerts 30 newtons on A, and A exerts 30 newtons on B. So this is related to Newton's third law. For every action force, there's an equal and opposite reaction force. If you push against a wall with a force of 100, the wall pushes back on you with a force of 100. So likewise, the force that A exerts on B is 30, and there's an equal and opposite force that B exerts on A, which is also 30. So those two forces, they're going to be the same. They have the same magnitude, but the direction is opposite to each other. Let's try another example like this so you can understand the concept. So this time we're going to have 3 blocks. We're going to call the first block block A, and then this is B and C. The first block is going to have a mass of 30 kilograms. The second is going to be 20, and the third is 10. So we're going to apply a force of 120 newtons. So go ahead and calculate the force that A exerts on B and the force that B exerts on A. Also, find the force that B exerts on C and the force that C exerts on B. So F equals ma. The total mass of the system is 60. So 120 divided by 60 gives us a net acceleration of 2 meters per second squared. Now our next step is to find the net force on each block using m times a. So 30 times 2 is 60. 20 times 2 is 40. And 10 times 2 is 20. So let's find the force that B exerts on A. So A feels a force of 120 newtons to the right. If the net force is 60, then the force that B exerts on A must be 60. What you need to do is subtract 120 from 60 So that means A feels a force of 60 newtons directed to the left. Now B feels the same force of 60 newtons to the right. And 60 minus 40 gives you 20. So that means that there must be another force of 20 newtons that slows B down to the left. B feels a force of 60 newtons that propels it to the right, but a force of 20 that slows it down. That's why it has a net force of 40. So the force that A exerts on B is this force, which is 60, and the force that B exerts on A is 60 as well. B slows down A, and A accelerates B. Now the force that B exerts on C is equal to this force. They're equal but opposite in direction. So B accelerates C with a force of 20 newtons. It pushes C 20 newtons forward. And then C pushes back on B with a force of 20 newtons. And so that's how you can figure it out. So to find these two forces is simply 120 minus 60. Now to find these two forces, the force that B exerts on C and C exerts on B, it's simply the force that A exerts on B and B exerts on A minus the net force on B. That's going to give you the 20. Now what if you have two blocks like this? Let's say this is block A and block B. And let's say that block B has a mass of 100 kilograms and block A has a mass of 50 kilograms. Now the gravitational acceleration is 9.8, but just to keep the numbers nice and easy to deal with, let's say G is approximately 10. Let's just round it. So what is the force that B exerts on A, and what is the force that A exerts on B? And also, what is the force that the surface exerts on B, and what force does B exert on a surface? So let's start with the surface. We can treat this as an object with a single mass of 150. So the force that the surface exerts on B is the normal force. The combined weight force of A and B is 150 times 10. So the weight force is 1500. So the normal force, which is the force that the surface exerts on B, that's also 1500. Now, what about A? What force does A exert on B and B exerts on A? Well, B has a surface just like this horizontal surface. So what we can do is ignore B and simply view it as a problem where we only have one box. So B is the surface and here's A. So the weight force of A is 50 times 100, which is 500. So therefore the normal force must also be 500. The normal force is equal to mg for a flat horizontal surface. So therefore we could say that the force that B exerts on A is the normal force of this surface, which is 500 newtons. So the force that A exerts on B is the weight force of block A, which is also 500. So that's how you can analyze this example. And the force that the surface exerts on B, we said was 1500. And the force that B exerts on the surface is the weight force of the two objects, which is a downward force of 1500 newtons. So that's what you can do to answer a question where you have a block on top of a block. Now let's talk about friction. So what exactly is friction? Friction is a force that opposes motion. So if you have an object moving this way, the frictional force is directed to the left. Now, if the object is moving to the left, the frictional force is directed to the right. Friction always works in such a way to slow down an object to rest. As one surface brushes against another or slides past another, you have friction. Whenever you have two surfaces sliding past each other, you have kinetic friction. Static friction occurs when those two surfaces are not sliding past each other. To calculate kinetic friction, it's equal to the coefficient of kinetic friction, mu k, times the normal force. The static friction is less than or equal to mu s, the coefficient of static friction, times the normal force. And keep in mind, for a flat horizontal surface, the normal force is equal to the weight force. So we could say that the normal force is equal to mg. As long as you're not pressing the object down against the surface, which will cause the normal force to increase, and if you're not pulling it up with a rope, which will cause the normal force to decrease. If you don't have any of those circumstances, the normal force is simply mg. Now, consider this situation. This is going to help you to understand the concepts of kinetic and static friction. So on the left, we're going to have an applied force. So if we apply a force to the right on the box, there's going to be a frictional force that opposes the motion. So let's make a table. So here we're going to have applied force, the kinetic frictional force, static friction, and net force. Now let's say if the mass of the object is 20 kilograms, and let's say mu k is 0.1 and mu s is 0.3. What is the kinetic friction and static friction if we apply a force of 0? If you don't apply any force, there's not going to be any friction or static friction, so the net force is 0. Now, what if we apply a force of, let's say, 5 newtons? What's the friction? What's F of k, the kinetic friction, and F of s, the static friction? So let's calculate it using the equation. So first, what's the normal force? The normal force is mg. So let's say g is 10 instead of 9.8. 20 times 10 is approximately 200 newtons. So now we could find F of k and F of s. So F of k is mu k times the normal force. So that's 0.10 times 200. 0.10 is basically 10%. 10% of 200 is 20. So F of k is 20 newtons. Now if you use the equation for F of s, where it's less than or equal to mu s times normal force, F of s is going to be 0.3 times 200. Now if 0.1 times 200 is 20, 0.3 times 200 is 60. That's 30% of 200. So now that we have F of k and F of s, what number should we put here? Is F of k 20 or is it something else? Now, you need to understand that if the applied force is 5, F of k is not 20. Here's why. Let's assume if F of k was 20. If we apply a 5 Newton force to the right, and if friction applies a force of 20 newtons, that would mean that friction is accelerating the object to the left. And imagine if you put a block on a table and it just all of a sudden just moves to the left. That's not possible. So friction can't be greater than the applied force. So therefore, the kinetic friction is zero. It doesn't exist at this particular instance. So what this means is that the block is not moving. The only time F of k applies is if the block is moving, if the two surfaces are sliding past each other, which we don't have. Since the block is not moving, what we do have is the static friction. Now, what is the static friction? Is it 60? The static frictional force cannot exceed the applied force. If we have an applied force of 5, and if the static friction is 60, the block will again begin to accelerate to the left on its own, which shouldn't happen. Notice that for static friction, we have an inequality. It's less than or equal to 60. So static friction has a maximum value of 60. It's going to match the applied force until you exceed that barrier of 60. So if you apply a force of 5, the static friction will be 5. So the net force is 0, the block doesn't move. Now if you think about it, let's say if you have a very large box with a bunch of stuff in it on a carpet. If you try to push the box, initially the box won't move. You're going to feel that resistance. It's going to be resistant to movement. Now eventually, as you increase your applied force, the box will eventually slide against the carpet and it will begin to move. And once it's moving, it's going to be easier to keep it moving. The reason why it's so hard to get it started is because static friction is usually greater than kinetic friction. So it takes a lot of force to get it moving. But once you get it moving, kinetic friction takes over and it's easier to keep it moving. So what's going to happen if we apply a force of 15 newtons? The static frictional force is 15, so it's not moving, there's no kinetic friction. If we apply a force of 20, let's increase it to 50. So the static friction will be 50, there's no net force. If we apply 60, the static friction will be 60, there's no net force. Now once we exceed 60, let's say if we go up to 70, we've exceeded static friction. So the block will begin to slide. So static friction is 0 because it's no longer stationary. The block is no longer at rest. So kinetic friction takes over, and kinetic friction is a constant 20. So 70 minus 20, the net force is now 50. Now, let's say if we increase the applied force to 100. It's going to be moving, so there's no static friction, but we still have a kinetic friction which has a constant value of 20 once it begins to move. So 100 minus 20, the net force is 80. So I hope that this example helps you to understand the concept of static friction and kinetic friction. What you need to know is that as you apply a force, you're going against static friction. Once you apply a force that's greater than 60, you have overcome static friction, the block begins to slide, and then you need to overcome kinetic friction. As long as you maintain a force above 20, the box or the block is going to continue to slide. So once you exceed static friction, you could drop your force down to the force, you can bring it down to 30, 40, 50. It doesn't matter. As long as it's above 20, it's going to keep moving. So let's work on some example problems. Let's say if we have a 30 kilogram block, and let's use a gravitational acceleration of 10 instead of 9.8. And let's say that mu k is 0.20 and mu s is 0.50. So now if we apply a force of 100 newtons, what is the acceleration of the object? Feel free to work this example. Now the first thing we need to do is we need to figure out, is it moving? So let's find the normal force first. The normal force is equal to mg. So it's going to be 30 times 10, which is 300 newtons. So from that we could find F of k, which is mu k times normal force, or 0.20 times 300. So what's 20% of 300? 10% is 30, so 20% is 60. So F of k is 60 newtons. Now what's F of s? What's 50% of 300? That's 150. So notice that the applied force has not exceeded static friction. So therefore, the acceleration is 0. Static friction at this point is 100. It's going to match the applied force until you exceed 150. So there's no net force. Now let's increase the applied force. What if the applied force, let's say it's 210 newtons? What is the acceleration at this point? So notice that the applied force exceeds static friction. So we no longer have to worry about static friction. We simply have to use kinetic friction. So the kinetic friction is 60. So what is the net force? The net force is the difference between the applied force and the kinetic frictional force. So it's 210 minus 60, which is 150. Now that we have the net force, we can find the acceleration. So the acceleration is going to be the net force divided by the 30 kilogram block. So this object will begin to accelerate at a rate of 5 meters per second squared. Now here's another example. Let's say if you're applying a force and the object is moving at a constant speed of 30 meters per second, and it's let's say it's a 50 kilogram object, and because it's moving, we don't need static friction. So let's say mu k is 0.20. What is the force applied on the block? Now, how would you answer this question? Feel free to pause the video and work out this example. So remember, the object is moving at constant speed, you're applying a force, and we have kinetic friction. What is the applied force? In this example, whenever an object is moving at constant speed, the acceleration is 0. So if we write the equation for net force, the net force is the difference between the applied force and the frictional force. And net force is ma. But because the acceleration is 0, the net force is 0. So therefore, the applied force must be equal to the kinetic frictional force. So if we move this to the other side, we can see that F of k is equal to F. So if we can find the frictional force, we can find the applied force. So the frictional force is mu k times the normal force. And mu k is 0.20, normal force is mg, the mass is 50, the gravitational acceleration is 10. So what's 0.2 times 10? Whenever you multiply a number by 10, you simply need to move the decimal 1 unit to the right. 0.2 times 10 is 2. 2 times 50 is 100. So the applied force in this example is 100 newtons. In order to move an object at constant speed, the applied force must be equal to the frictional force. So now let's move on into our next topic, and that is inclines. So let's say if we have a block on this incline, what are all the forces acting on the block? So we have a normal force that is perpendicular to the surface, and we have a weight force, mg, and there's some other forces too. There's a component of gravity that pulls down this object down the incline. We'll call it Fg, and because it wants to slide in that direction, potentially we have friction if it's not a frictionless surface. So it could be kinetic friction or static friction, depending on if it's sliding or not. Now, let's draw a triangle. The angle theta is equal to this angle. Here's why. Let's say if this is 30, this is 90, this is 60, and this part forms a 90-degree angle, which means this part is 30. Therefore, this is theta, this is going to be theta. So now, what is this side with respect to mg? What is that equal to? Notice that it's the adjacent side relative to this angle. So this portion is equal to mg cosine theta. It's the hypotenuse times cosine theta. Now what about this part of the triangle? Notice that it's opposite to theta, so it's associated with sine. This is mg sine theta. Notice that the normal force is completely opposite to this component of gravity. So therefore, the normal force on an incline is equal to mg cosine theta. This is an equation that we're going to use a lot, so make sure you commit it to memory, but also it helps if you can understand how to get it from the free body diagram. Now notice that FG is parallel to this part of the triangle, so FG is equal to mg sine theta. That's another equation that you need. So remember these two equations. We're going to use it to solve a lot of problems. Now let's say if we have a frictionless incline and the angle of the incline is 30 degrees. And we have a 20 kilogram block. What is the acceleration of the block down the incline if there's no friction? So what's the first thing that we need to do? In order to find the acceleration, we need to find Fg. This is the only force that's accelerating the block downward. The net force parallel to the incline is equal to F of g, since that's the only force that's pulling the block downward. The net force is equal to ma, and F of g is mg sine theta. So we really don't need the mass in this equation. We can cancel m. So the acceleration is simply g sine theta, which we're going to use g as 10, and sine 30 is 1/2. So the acceleration is 5 meters per second squared. Now let's say if the length of the incline, let's say it's about 100 meters long. What is the final velocity once the block slides down to the end of the incline? What's the final velocity at this point? So what equations would you use to figure that out? So we know what the initial velocity is. We're going to assume that the block accelerates down the incline from rest. So the initial speed is 0. We need a final speed. The distance that it travels down the incline is 100 meters. And we know the acceleration. The equation that we need is this equation. V final squared is equal to V initial squared plus 2AD. So we're looking for V final. V initial is 0. The acceleration is 5, and D is 100. So 2 times 5 is 10, and 10 times 100 is 1,000. So to solve for V, we need to take the square root of both sides. So V final is equal to the square root of 1,000, and that's about 31.6 meters per second. So now that it reaches the bottom of the incline, so it's at this point right now, and it's moving forward with a speed of 31 meters per second. Now let's say that the horizontal surface has friction, And let's say the coefficient of kinetic friction is 0.20. How far will the block travel until it comes to rest? So if it comes to rest, we know the final speed is 0, but the new initial speed is 31.6. So what can we do to find the stopping distance? So once it's on the horizontal surface, friction is going to slow it down. And friction is the only force acting on it. It's no longer on the incline, so Fg no longer acts on it. So therefore, the net force is equal to the kinetic frictional force. So Ma is equal to Fk, and Fk is mu k times normal force. And the normal force on a horizontal surface is simply mg. So we can cancel m. So the acceleration is equal to mu k times g. So mu k is 0.20, and g we're going to use a rounded value of 10. So the acceleration is 2 meters per second squared. Now keep in mind, this is a deceleration value because friction is going to slow the object down to a stop. So we can put a negative sign if we want. We could say it's negative 2 meters per second squared, since it's opposing the motion of the object. Now that we have the acceleration, what equation can we use to find the stopping distance? The equation that we need is the same one. It's v final squared is equal to v initial squared plus 2ad. We're just looking for d in this particular problem. So the final speed is 0. The initial speed is 31.6 squared plus 2 times a negative acceleration of 2 times the distance which we're looking for. So right now what we have is 31.6 squared minus 4d is equal to 0. I'm always out of space. So let's move negative 4d from the left side to the right side. So 31.6 squared is equal to 4d. So d is equal to 31.6 squared divided by 4. So that's going to give you a value of 249.6 meters. So that is the distance that the object travels before it comes to rest. Now, let's try another example. Let's say if we have a block, and it's a 10 kilogram block. This time, there's going to be friction on the incline. Let's say mu k is 0.10 and mu s is 0.30. And let's say the angle is 30 degrees. So, will this object slide down or will it remain at rest? What's the answer? So we need to calculate f of g, which will accelerate the object down the incline. Now keep in mind, we still have the frictional force. If it's moving, it's f of k. If it's not moving, it's f of s. We need to find out which frictional force is active on this block. So the next thing we need to calculate is the normal force. The normal force is equal to mg cosine theta. So the mass is 10, g is 10, and we have cosine 30. So it's 100 cosine 30, and so you should get about 86.6 newtons for the normal force. So with that, we could find f of k and f of s. So f of k is equal to mu k times the normal force. So that's going to be 0.10 times 86.6, which is about 8.66 newtons. And the static frictional force is less than or equal to mu s times the normal force. So that's 0.30 times 86.6, which is about 25.98 newtons. So now we need to calculate f of g. If f of g exceeds f of s, it's going to slide down. If not, it's going to remain at rest. F of g is equal to mg sine theta. So that's going to be 10 times 10 times sine of 30, which is 100 sine 30, and sine 30 is a half, so f of g is equal to 50 newtons. So f of g exceeds the static frictional force, therefore the object will slide down. So with this information, how can we calculate the acceleration? So if it's sliding down, f of s is not active. We don't have to worry about it anymore. So the first thing you need to do is write an equation for the net force. So along this direction, parallel to the incline, there's only two active forces we have to worry about, f of g and f of k. The net force is the difference between f of g minus f of k in this particular example. So the net force, which is ma, that's equal to mg sine theta minus mu k times the normal force, which the normal force is mg cosine theta. So we can cancel m because every term has an m within it. So the acceleration is g sine theta minus mu k g cosine theta. So we can factor out g if we want. So it's sine theta minus mu k cosine theta. So g is 10, and then we have sine 30 minus mu k, which is 0.10 times cosine 30. So sine 30 is 0.5. Cosine 30, that's 0.866 multiplied by 0.10, that's 0.0866. So 0.5 minus 0.0866, you should get 0.4134, and therefore the acceleration is going to be 4.134 if you multiply it by 10. So the acceleration down the incline should never exceed the gravitational acceleration, which is 9.8, or if you round it to 10. So if g is 10, you should never have an answer greater than 10. Now let's say if we have another incline and a box is placed on it, and we have an angle theta. At what angle will the box begin to slide? Now let's say if it's initially at rest and theta is increased. It could be 30, it might increase to 40, but what's going to happen as you increase theta? Eventually, at some point, Fg will exceed the static friction F of s. Once that happens, the box will begin to slide. Keep in mind, Fg is proportional to the sine theta. So as theta increases, sine theta increases, therefore Fg increases. And once f of g exceeds f of s, it will begin to slide. So how can we calculate the minimum angle at which the box begins to slide? The critical point is when f of g equals f of s. at any point higher than that. If f of g is just a little bit higher than f of s, it will begin to slide. So the critical point is when they're equal. So f of g is mg sine theta. F of s is mu s times normal force, and the normal force on the incline is mg cosine theta. So notice that we can divide both sides by mg. So these two terms will cancel. Now, if we divide both sides by cosine theta, we can see that mu s is equal to sine theta divided by cosine theta. Sine theta divided by cosine theta is equal to tangent theta. So if you solve for theta, theta is equal to the inverse tangent of mu s. This is the formula that you need to find the critical angle at which the box begins to slide against static friction. So let's say mu s is 0.25, because I forgot to give that value. So therefore theta is equal to inverse tangent 0.25. So at an angle of 14 degrees, the box will begin to slide. That's the critical threshold point. So now let's work on some pulley problems. So let's say if we have a surface and we have a block on the surface but without friction, and we have another block. Now let's say this block is 20 kilograms and this one is 10. So if there's no friction at all, what is the net acceleration of the system? So the first thing we need to do is calculate the net force. The only force that's active in pulling the system to the right is the weight force of the 20 kilogram object. We'll call it W. So let's also call this M1 and this mass M2. The weight force is M1G. The net force is equal to the total mass of the system, M1 plus M2, times the acceleration of the system. Now the reason why we have to use the total mass is because the weight force, or M1G, it has to pull both the 10 kilogram object and the 20 kilogram object in this direction. So if the 10 kilogram object wasn't there, this object will fall at an acceleration of 10. But because the 10 kilogram object is there, it's going to slow the descent of the 20 kilogram object. So you have to incorporate M2 somehow into this equation. So for these pulley systems with multiple masses, typically the net force is MA, but M represents the total mass of the entire system. Blocks M1 and M2 will both move with an acceleration of A at the same rate. So let's say if the acceleration for block 1 is 3 meters per second, block 2 has to move at that same rate because they're connected by means of the same rope. But now let's go ahead and calculate the acceleration. So for this particular problem, it's M1G divided by M1 plus M2. So it's the weight force divided by the total mass of the system. So it's 20 times 10 divided by 10 plus 20, which is 30. So we can cancel a 0. So 2 times 10 is 20. So it's 20 over 3, which is about 6.67 meters per second squared. So at this point, how can you calculate the tension force in the rope now that we have the acceleration of the system? So what is the tension force that slows the descent of the 20 kilogram object? And what is the tension force that pulls the 10 kilogram object to the right? So let's calculate the net force of each block. The net force for the 20 kilogram block is going to be 20 times the acceleration of 6.67. So the 20 kilogram block, it feels a net force, a downward force of 133.4 newtons. Now keep in mind the weight force is 20 times 10, it's mg. The weight force is 200. So the difference between these two forces is equal to the tension force. So 200 minus 133.4 gives you a tension force of 66.6. So to make sense of this value, we have a downward force of 200, an upward force of 66.6. So if you do 200 minus 66.6, you're going to get a net downward force of 133.4. Now let's focus on the second object, the 10 kilogram object. So if we multiply 10 by 6.67, we have a net force acted on the 10 kilogram block that's equal to the tension force. These two values are the same, therefore the tension forces are equal, which they should be since they're acting on the same rope. And so you know that you've done the problem correctly if these two have the same value. So now let's try another problem, but in this case we're going to have friction. So let's use the 20 kilogram block again and a 10 kilogram block. And the friction along that surface, the coefficient of kinetic friction, we're going to use 0.20, and the static friction, the coefficient is going to be 0.40. Under these conditions, will the system remain at rest, or will the blocks move? If they do move, what is the acceleration of the system? So we need to find f of s. F of s is less than or equal to mu s times the normal force. And since the block, which is exposed to friction, that's a 10 kilogram block, since it's on a horizontal surface, the normal force is simply equal to mg. So mu s is 0.40, and m is 10, and g is also 10. So 10 times 10 is 100 times 0.4. So the static frictional force has a maximum value of 40 newtons. So friction is going to oppose the direction of motion. The blocks wants to move this way, so friction is directed to the left. It's always opposite to the direction of motion. Now we need to find the weight force. The weight force is going to be mg, which is 20 times 10. So the weight force is 200 newtons. Notice that the weight force exceeds the static frictional force. The weight force is what drives the system to the right. Because it's greater than the static frictional force, it's going to move. So now we got to find f of k, because once it's moving, f of k takes over. So f of k is mu k times normal force. So it's 0.20 times mg, or times 10 times 10. So f of k is 10 times 10 is 100 times 0.2, that's 20. So we have 20 newtons for f of k. So now we need to write the equation for the net force. Net force is equal to the difference of the weight force minus the kinetic frictional force. The weight force pulls the entire system to the right, but friction slows it down. So because these two vectors are in opposite directions, we need to subtract those two values. The net force is MA. The weight force is M1G. Let's call this M1, and this is going to be M2. Now, F of K, we know it to be mu K times the normal force of mg, but it's going to be m2g. So we know the weight force. Oh wait, by the way, we need to replace the net force with the total mass of the system. So it's m1 plus m2 times A. Let's not forget that part. So to solve for A, it's going to be m1g minus mu k m2g divided by m1 plus m2. So for this particular problem, when you have friction, this is the equation that you need to find the acceleration. For those of you who simply want to memorize the equation for each scenario, there you go. But now let's get the answer for this particular problem. So m1g is basically the weight force. It's 20 times 10, which is 200. Mu k m2g, that's 0.20 times 10 times 10, which is f of k. So that's 20. And then m1 plus m2, that's 10 plus 20. So don't forget to divide by the total mass of the system, not just the individual masses. So the difference is 180. That's 200 minus 20. 10 plus 20 is 30. So we can cancel 0. 180 over 30 is the same as 18 over 3. 18 divided by 3 is 6. So the acceleration of the system is 6 meters per second squared. So notice that it's always less than 10 if there's an object that slows down the descent. So now that we have the acceleration of the system, let's calculate the tension force. Feel free to try that yourself. So I'm going to put the acceleration over here. So the first thing we need to do is find the net force acting on each block. So what is the net force acting on the 10 kilogram object? It's going to be m times A, 10 times 6, which is 60. So we have a net force of 60 newtons. Now the weight force we know to be 200, but what is the net force on this block? It's 20 times 6. 20 times 6 is 120. So there's a net downward force of 120. So if we have 200 newtons going down and the net force is 120, there must be an 80 newton force that slows down the descent of the 20 kilogram object, because a downward force of 200 newtons minus an upward force of 80 newtons will give you a net downward force of 120. So this upward force is the tension force. So we can see that the tension force is 80. Now, how is that possible? Is that answer correct? Because this force is 60. In the last example, these two forces were equal. So what's going on here? Is the tension force 60 or is it something else? Now, whatever you do, don't forget about friction, because we still have friction. Remember, the frictional force was mu k times mg. Mu k was 0.20 and mg was 100. So the frictional force is 20. So the tension force that pulls the 10 kilogram object to the right must not only accelerate it with a force of 60 newtons, but it must overcome the frictional force of 20. Keep in mind, the 60 is the net force acting on the 10 kilogram object. If you focus on the 10 kilogram object, it's being pulled to the right by an 80 newton tension force, which is slowed down by the 20 newton frictional force. So 80 minus 20 gives you a net force of 60. And as you can see, the two tension forces are equal. So we know that we've done the problem correctly. The tension is 80, the acceleration is 6, everything works out. Now let's consider another problem. Let's say if we have a pulley and two blocks. Now if the blocks have the same mass, they're going to remain stationary. But let's say if this block has a mass of 20 kilograms and the one on the left is 10 kilograms. Let's call this M1 and M2. And let's say there's no friction at all in this system. What is the acceleration of the entire system, and what is the tension force in the ropes? Feel free to pause this problem and see if you can answer the question. So we know the system is going to move in this direction. And the only force, well, there's two forces acting on this system. We have the weight force of M2, so that's M2G, that's about 200 newtons, that pulls in that direction, and also the weight force for M1 because it's under the influence of gravity, and that's about 100 newtons. So because the weight force on the right is greater than that on the left, the system is going to move this way. But now for these problems, we always need to write an equation for the net force. The net force is the difference between M2G and M1G. And the net force is mass times acceleration, but the total mass. So it's going to be M1 plus M2 times the acceleration. And that's equal to, if we factor out G, it's going to be G times M2 minus M1. So to solve for A, we need to divide both sides by M1 plus M2. So the acceleration is going to be G times the difference of the two masses divided by the sum of the two masses, M1 plus M2. So that's how you can find the acceleration of this system if there's no friction, if you want to save that equation for an upcoming test. So let's calculate the value of the acceleration. So G is 10, M2 is 20, M1 is 10, and on the bottom it's going to be 10 plus 20. So 20 minus 10 is 10, so we have 10 times 10 and 30 on the bottom. So we can cancel a 0, so then it's 10 times 1 divided by 3. So the acceleration of the system is about 3.3 meters per second squared. So now that we have that information, what is the tension force? How can we calculate it? So the first thing we need to do is find the net force acted on each block. The net force acted on the 20 kilogram block is going to be the mass of the 20 kilogram block times the acceleration. So keep in mind, even though I wrote 3.3, it's 3.3333 repeating. If you multiply that by 20, you should get a number approximately about 66.7 newtons. So that's the net force. Now keep in mind, there's an upward tension force that slows the descent of the 20 kilogram object. So 200, the downward force, minus the net force, is going to give you the tension force, which is about 133.3. Now what about the other block? What is the net force? The net force is the mass times the acceleration, 10 times 3.3, which is about 33.3. Now, is the net force in the upward direction, or is it in the downward direction? Remember, the system is moving in this direction. that means that the 20 kilogram block is descending, but the 10 kilogram block is ascending. It's going up. So the net force for the 10 kilogram block is in the upward direction, so that's positive 33.3 newtons. So now, what is the tension force? Notice that the tension force is 133.3. It's greater than 100 because not only does it have to support the weight of the 100 Newton object, but it also must lift it up with a force of 33.3. So that's why T is 133.3. Now, if this situation confuses you, let's analyze each block one at a time. So let's start with the 20 kilogram block. There was an upward tension force of 133.3 newtons, and there was a downward weight force of 200 newtons. And the net force, because the 20 kilogram block was descending, the net force was equal to 66.6 newtons, or we'll say 66.7. Now let's focus on the signs of everything. So the sum of the forces in the y direction is going to be the tension plus the weight force. Now in some earlier examples I might put T minus W because the weight force is going in a downward direction. At some point you have to incorporate a negative sign. So you can write the equation as T plus W, but when you plug in the numbers, make sure that you put in negative 200 for W because it's going in the negative y direction. So 133 minus 200 gives you negative 66.7, which is the net force. The net force and the sum of the forces in the y direction are the same. The negative sign simply tells you that the object is descending with a net force of 66.7. The net force is in the negative y direction. And now let's analyze the 10 kilogram block. So there's an upward tension force of 133 newtons and a downward weight force of only 100 newtons. So because the tension force exceeds the weight force, we can clearly see why there's an upward net force of 33.3 newtons. And it makes sense because that's why the 10 kilogram block accelerates upward, because the tension force exceeds the weight force. If we write an equation, the net force is tension plus weight force. Tension is in the upward direction, so it's positive 133.3. The weight force is in the downward direction, so it's 100, but negative 100. So the net force is positive 33.3. And so that's why it's in the upward direction. So anytime the tension force exceeds the weight force, the block will accelerate upward. In the other example, the tension force, which was also 133 newtons, was less than the weight force. And so the 20 kilogram object descended in a downward direction. And the net force was also in the downward direction, and it had a value of negative 66.7. So I just want you to understand how these forces relate to each other and why they work the way they do. So if the net force is positive, the object is accelerating in the upward direction. If it's negative, it's descending in the downward direction. Here's the next situation. This time we're going to have an incline, a pulley, and two objects. So we're going to have a 20 kilogram object and a 10 kilogram object, but no friction in this example. Let's say the angle of the incline is 30 degrees. Now, which direction will the object accelerate? Will it accelerate in this direction, or will it accelerate in this direction? So without friction, there's only two forces that you need to compare. The weight force of the 20 kilogram object, which causes it to descend in a downward direction, and F of G, the component of the weight force for the 10 kilogram object that's parallel to the incline. Now intuitively, you know that the weight force exceeds the F of G force because the mass of the 20 kilogram object is much greater than the mass of the 10 kilogram object. So we know it's going to go in this direction. But we can just calculate it to make sure. So the weight force is going to be mg, which is 20 times 10. So this weight force is 200 newtons. Fg is mg sine theta. So m is 10, g is 10, and we have sine of 30, which is 1/2. So that's going to be 100 times 0.5. So F of G is about 50 newtons. So now that we know the direction of motion, we can calculate the acceleration of the system. So let's write an equation for the net force. So the net force is the difference between the weight force, which wants to cause the system to move to the right, minus F of G, which wants the system to move to the left. The net force is going to be ma, but using the total mass. So m1 plus m2 times a is equal to w minus F of G. So the acceleration is the weight force. Let's call this m2, and let's say this is m1. So the acceleration is going to be m2g minus F of G, which is m1g sine theta, divided by the total mass, m1 plus m2. So you can save this equation if you want to. So now let's calculate the acceleration. So m2g, that's 20 times 10, which is 200. m1g sine theta, we can see that is 50. So the difference between the two forces is 150, divided by the total mass of 30. So 150 divided by 30. We could cancel the zeros, and 15 divided by 3 is 5. So 5 is the net acceleration of the system. Now the last thing we need to do in this particular example is calculate the tension force. So let's find the net force as we've been doing before. So with the 20 kilogram block, it's going to be 20 times 5, m times a. So this block has a net downward force of 100 newtons. So therefore, 200 minus 100 means that there's an upward tension force of 100. So now what is the net force of the 10 kilogram object? It's 10 times 5. So it feels a net force of 50 newtons to the right because there's a tension force of 100. Keep in mind the net force is due to the difference of the tension force and F of G, which is 50. So you have 100 newtons to the right, that's the tension force, minus 50 for F of G to the left. And so there's a net force of 50 newtons to the right if you do 100 minus 50. And for this object, it experiences a downward force of 200 and an upward tension force of 100. So 200 minus 100 is 100, and so you have a net downward force of 100. In either case, the tension forces are equal and everything is balanced, so we have the answer. Now we're going to have the same situation, no friction, but this time the 20 kilogram block is on the incline and the 10 kilogram block is over here, and the angle is still 30 degrees. So will the system remain at rest, or will it accelerate to the left or to the right? So the weight force of this block is mg, so that's 100. And F of g is mg sine theta, which is 20 times 10 times sine of 30. And so it's 200 times sine of 30, which is a half. So that's 100. Notice that in this particular example, F of g is equal to the weight force. So in this case, the system remains at rest. The two forces balance each other, and so there's no net movement. Now here's a question for you. Let's say if we have a 30-kilogram object and a 10-kilogram object. At what angle theta will the system remain at rest? If the angle is very large, F of g will exceed the weight force. And when F of g exceeds the weight force, it's going to go to the left. If the angle is too small, the weight force will exceed F of g, and it's going to go to the right. So what is the angle at which the system remains at rest? To find that angle, we need to set F of g equal to the weight force. So mg sine theta, let's say this is m1 and this is m2. So m1 g sine theta is equal to m2 g. We can cancel g. So sine theta is equal to the ratio of m2 over m1. So theta is equal to the inverse sine of m2 divided by m1 if there's no friction. So let's find the answer. So what is the inverse sine of m2, which is 10, divided by m1, which is 30? So the inverse sine of 1/3 is about 19.5 degrees, or 19.47. So at this angle, the system is at rest. If theta exceeds 19.5, F of g is going to be greater than W, and the system is going to move to the left. Now, if theta is less than, let's say, 19.4 or 19.47, the system is going to move to the right. The weight force will exceed the F of g force. So by adjusting the angle, you can determine what direction it's going to shift to. Now let's say if we have a 30-degree angle, a 20-kilogram block, and a 30-kilogram block. But this time we have friction along the incline. So let's say there's friction here. And let's say mu s is 0.30 and mu k is 0.10. So will the system remain at rest, or is it moving? And if it's moving, what direction is it moving to? So let's calculate the forces. The weight force for the 20-kilogram object is 200 newtons. F of g, which is mg sine theta, that's the mass, that's the 30-kilogram object, times g, times sine of 30, which is 1/2. 30 times 10 is 300. Half of 300 is 150. So we have a force of 150 going in this direction. So without friction, the weight force exceeds F of g. So without friction, it would go this way. But if static friction is 50 newtons or more, the system will be at rest. If F of S is less than 50, then the 200 Newton force will be more than enough to compensate for F of G plus the frictional force. So we have to calculate F of S. So F of S is less than or equal to mu S times the normal force, which on an incline is mg cosine theta. So mu S is 0.30. The mass is the 30 kilogram block that's on the incline. G is 10 times cosine 30. So 30 times 10 is 300 times cosine 30, that's 259.8 times 0.3. So F of S is less than or equal to 77.9. So if the block were to move this way, the block has to overcome the 150 Newton plus a static frictional force of 77.9. So it's not going to happen. We need a weight force of 227.9 to get the system moving. So the acceleration of the system is 0. Now, if the acceleration is 0, if the whole system remains at rest, what's the tension force? So if this block is not moving, the net force is 0, which means that the weight force must equal the tension force. So the tension force is 200 newtons. That would mean that the tension force here also has to be 200 newtons. So therefore, what is the static friction? Remember, the static frictional force can be anywhere from 0 to 77.9. The 77.9 is simply the maximum value, but it doesn't have to be there. We know the tension force has to be 50. I mean, not 50, but 200. The tension force in a rope is always the same. If this is 200, this has to be 200. So if the 30 kilogram block has an upward tension force of 200 and a downward F of G force of 150, that means that the frictional force is only 50. It's just enough to keep the system at rest. So these two forces must balance out with the tension force. And so the net force of the 30 kilogram object is 0. 200 minus 50 minus 150 is 0. And the net force of the 20 kilogram object is 0. 200 minus 200 gives you 0. So everything is at rest in this particular case. Now let's use the same angle of 30 degrees. This time, the mass of the first block is 50, and this is going to be 20. Mu k is going to be 0.10, and mu s is going to be 0.20 for this problem. So in which direction will the system move? To the left or to the right? Or will the system be at rest like the last example? So let's calculate the forces. The weight force is 200 newtons, and F of G, that's going to be mg sine theta, so 50 times 10, and sine 30 is 0.5. So 50 times 0.5 is 5, that's half of 10. 10 times 0.5 is 5. That's half of 10. And 50 times 5 is 250. Or if you did 50 times 10, that's 500. Half of 500 is 250. So F of G is going to be 250 in this case. So the system can't go to the right. It's not going to happen because the weight force is less than the F of G force. So it appears as if the system is going to go to the left. But we have to take into account friction. Because this force is greater, it's likely that the system might go to the left. So if it moves to the left, in what direction will static friction be directed? Friction opposes motion, so F of S is going to go against the 250. So the 250 has to not only support the weight of the 20 kilogram object, but it has to overcome static friction. So static friction has to be less than the difference between 250 and 200. If f of s is less than 50, the objects will move to the left. If f of s is greater than 50, then the system will remain at rest. So let's find out what situation we have in this example. So mu s is 0.20 times normal force, which is mg cosine theta, or 50 times 10 times cosine 30. So 50 times 10 is already 500 times 0.2, that's 100, times cosine 30, which is 86.6. So notice that this force is not enough to overcome static friction and the weight force. So once again, the system is at rest and the acceleration is 0, which means that this tension force is 200 and the tension force here is also 200. So notice that f of g is compensated, or it's balanced, by the tension force and the frictional force of 50. The frictional force doesn't have to go all the way to its maximum. It only needs to be 50 to prevent the 50 kilogram block from sliding downward, because 50 and 200 is enough to balance out the 250 f of g force that wants to bring the system in the downward direction. So here's the last example for the day. So this time we're going to have a 100 kilogram object, and on the incline it's going to be a 40 kilogram object. Mu k is going to be 0.10 and mu s 0.20. So will the system remain at rest or will it move? So the weight force is mg, 100 times 10, which is 1,000 newtons. F of g, which is mg sine theta, is going to be 40 times 10 times an angle of sine 30. So 40 times 10 is 400 times a half, that's 200. So we have a downward force of 200. So now let's find f of s. F of s, which is mu s, that's 0.20 times mg, 40 times 10 times cosine 30. So 40 times 10 is 400 times cosine 30, that's 346.4 times 0.20. So the static frictional force is 69.3. So clearly, this force is significantly larger than this force. So it appears as if the system is going to move to the right, which means friction is going to oppose motion, so it's directed to the left. Static friction and the 200 Newton force is not enough to stop this force, so it's going to move. So we no longer have static friction, we need to use kinetic friction. So let's calculate f of k. So f of k is mu k times mg times cosine 30. It's mu k times normal force. So 400 times 0.10 times cosine 30 gives us a value of 34.6 newtons. So that's f of k. So now what is the acceleration of the system? So we need to find the net force. The net force is going to be the weight force, which is 1,000, minus f of g, and also minus the kinetic frictional force. These two forces, they're going to slow down the system as the system moves to the right. So net force is going to be the mass times acceleration. Don't forget to use the total mass. The weight force, let's call this m1, and this is going to be m2. So the weight force is m1g, and f of g is going to be m2g sine theta, and f of k is mu k m2g cosine theta. So to write one final equation for the acceleration, hopefully I can fit it here, I'm going to factor out g. So it's going to be m1 minus m2 sine theta minus mu k m2 cosine theta divided by m1 plus m2. So you can save that equation for this situation if you want to. So g is 9.8, m1 is 100, m2 is 40 times sine 30, which is a half, minus mu k, that's 0.10, times m2, which is 40, times cosine of 30, divided by the sum of the two masses, which is 140. So let's type this in. 100 minus 40 times 0.5, that's 80, and 80 minus 0.10 times 40 cosine 30, that's 76.536 times 9.8, which is 750, divided by 140. And so the acceleration in this particular problem is about 5.36 meters per second squared. So now we can calculate the tension force. So let's find the net force first. So the net force for the 100 kilogram object is going to be 100 times 5.36. So we have a downward force of 536 newtons. So to find the upward tension force, it's 1,000 minus 536, and that's 464. Now the net force for the 40 kilogram object is 40 times 5.36. So the net force that the 40 kilogram object experience is 214.4 newtons. So the tension force that pulls the 40 kilogram object up must exceed, it must be strong enough to overcome the 200 Newton force plus the kinetic frictional force of 34.6, and it has to accelerate the 40 kilogram object up the incline by 214.4 newtons. So if we add those three values, I know I have a lot of circles, but I try to write it on the right side. If we add 200 plus 34.6 plus 214.4, well, you get about 449. So let's see what happened, because those numbers aren't exactly the same. They're close, but there's a small, minute difference. And I know what it is. It's the acceleration. Because before I used 10, but here I use 9.8. Let's change this to 10. So let's recalculate this value. Well, actually, that changes everything. So let's make this 10. We need to recalculate the acceleration. So 100 minus 40 times 0.5 minus 0.10 times 40 times cosine 30. We said that's 76.535 times 10 That's 765.36 divided by 140. So the acceleration is a little bit different. It should be 5.47. Now, since we use a g value of 10 to calculate f of g and f of k, we need to use that same value. Otherwise, as you've seen in this example, our answers will be a mismatch. So now let's recalculate the net forces. So 100 times 5.47 gives us a net downward force of 547 newtons. So to calculate the upward tension force, it's 1,000 minus 547, which is 453 newtons. Now let's calculate the net force of the 40 kilogram block. So it's going to be 40 times 5.47, and you should get 218.8 newtons. So the tension force that pulls the 40 kilogram block up has to be strong enough to support the 200 newton force, the kinetic frictional force of 34.6, and also it has to move up the 40 kilogram block with an upward net force of 218.8. So it has to do a lot of work. So let's add these three values, and let's see if we get 453. So 200 plus 34.6 plus 218.8 is indeed 453.4, which is close enough. We can live with that. So just make sure you use the same acceleration. If you use 9.8, make sure you use it for all the calculations. Or if you use 10, then just make sure you use 10 for every value of g that you plug in. So that is it for this video. Thanks for watching, and I hope you have a better understanding of forces like tension force, normal force, pulley systems, friction, and that's all I got for today. So thanks for watching, and take care.